Good morning, everyone. Happy Wednesday. I hope everyone enjoyed a long day weekend. So now we're going to start chapter 16. So chapter 16 is aldehydes and ketones. All right, so let's first start with what we're looking at. So we're looking at roughly this carbonyl group here. So I'm just going to... Oh, that's why I'm struggling so much with my Wacom. Give me a second here. There we go. That's better. It's too sensitive. All right, so we're looking at this carbonyl group here, so roughly. And so some things about this carbonyl group is we have a pi bond here. And so the other thing that we're going to notice, I'll just put two generic R's there. So this carbon has a partial positive charge here. And this oxygen, of course, is electronegative. So you could draw a partial negative charge. But what you'll find is that this carbon is subject to nucleophilic attack. Excuse me, electrophilic. No, sorry, nucleophilic. Nucleophilic attack. So, meaning we're going to have something with a negative charge attacking this, meaning it wants something with a slightly positive charge. So this carbon is slightly positive. And then what we're going to notice, since it has this double bond, if this carbon gets attacked, these electrons can move over to the oxygen. And so this is also polar, a polar bond. The CO stretch is also extremely characteristic. I know we don't go into this, but I'll just say characteristic. So you can characterize this. Some techniques that we use for characterization are going to be IR and NMR, and IR would be very useful since carbonyls have a distinct stretch. So we've kind of mentioned, this dipole moment that CO has, and since it's a double bond, it also has a really strong bond. And so I just wanted to show one example. So this is ethyl acetate. So we've looked at ethyl acetate before. So it has our CO double bond. And then the CO stretches come up around the IR region, anywhere 16 to 1700. And this would also tell us how strong this bond is, depending on what frequency it oscillates at. And so that's a great way to characterize these compounds. And then, of course, we're just focusing on aldehyde and ketones, but there are many other groups that are either analogous or similar in structure to the CO. So, of course, formaldehyde just has two H's, so the simplest form here. Carboxylic acid. Don't forget this is when we have an OH there. Esters have an R group. Amides are also related. So amides can be interesting. So this nitrogen has these lone pairs here. And so these could actually go into a bond here in a certain scenario, moving these electrons up. So we have similar sort of movement there. Same with these enones. So this double bond can move. Those electrons can move up. And then acyl halides are also similar. So got this double bond here and then some halide. And acid anhydrides are also popular. And so, of course, carbonyls are found in nature. So this is octanol. And this is found in oranges. So octanol. And so now this brings us into naming. So aldehydes, again, take their name from the parent chain. And the ene is removed and changed with all. So we see this with octanol. So instead of octane, we add that all at the end. And so the aldehyde functional group is given the number 1 spot. And so that's not included in the name, and everything else would be dependent on that. And so the common names usually start with the common parent chain and add aldehyde. So let's look at a few. So this is cyclohexane carbaldehyde. We have our aldehyde, cyclohexane. So now this is in the 1 position. So this has to be 1. So 1, 2, 3. So 3-methyl cyclohexane carbaldehyde. So same thing with this one. This is in the 1 position. And then looking at this one, so we have trans 2-methyl cyclopentane carbaldehyde. This one looks funny. Yeah, I feel like this one's name is wrong. Because this is in the 1, so this would be in the 3. So I think this is supposed to be 3, 3. Because this is 1 and 2, so weird typo there. And then, so looking at the ketones, they also follow similar rules. So again, the ketones, now they're more in the middle, and so they take their ending, the E is removed and then replaced with "one." So this would be propanone, otherwise known as acetone. So this is a common name. And many of these have generic names. So this is acetophenone or methylphenylketone. And you can see this. So methylphenylketone. So this is known as benzophenone. So this is actually a really cool compound. So benzophenone is used as a color indicator to let you know when your solvent is dry, essentially. So this benzophenone, in the presence of a reductant, forms this benzophenone radical. So the sodium adds a proton here, and so it makes this compound. And I'll explain why it's super relevant in a second. So it forms this compound. And so this is a purple compound, and it is used as an indicator to let you know when your solvent is dry or not, essentially. And so this is really cool. So you put, and this is for drying solvents by hand, because if you're doing air-free chemistry, if you buy a solvent, even though it's, 99% pure or whatever, it still is water. And that water is significant when you're doing air-free chemistry. So to get your solvents water-free, you can add some sodium in there to dry them, at least with, most solvents. So now this is kind of going down the rabbit hole. But, THF, benzene, ether, all those can be dried with sodium. And then if you put some benzophenone in it, that acts as your indicator. And so it starts off, this like greenish, bluish color when you first start mixing it. But then it gets to this deep, deep purple. And that's when you know your solvent is dry, since it has formed this nice radical species everywhere. And so you know you're ready to distill. And so this is, so let's look at this. So 1, 2, 3, 4, 5. So pentanone there. Then the ketone's in the 2 position, so this would be 2-pentanone. We could also name it by its 2 sides. So methyl for this side, and then propyl for 1, 2, 3, ketone. So methylpropyl ketone. So for this next one, we can name it 2 different ways. So we could find our longest chain. So 1, 2, 3, 4. And then, so we have butane for that. It's in the 2 position. This methyl is in the 3. So 3-methyl-2-butanone, or again, naming it by its parts. So this is an isopropyl. That's a methyl. So methyl isopropyl ketone. And then, so this next one, so ethyl now for 2, and then propyl ketone, or 3-hexanone. So any questions about that so far? So some other properties, I feel like this has come up before. So boiling point of aldehydes and ketones. So what do you think their boiling points may be? Well, what kind of intermolecular forces do they have? Let's just think about that. And I just put acetone up there so we could think about it. And we said, well, the CO, right, that's going to be polar. So these tend to be polar. And so if they're polar molecules, they're going to have strong dipole-dipole forces. And so they tend to have higher relative boiling points by molecular weight due to polarity. And so just comparing so this compound versus this compound, this would have the higher boiling point. And so now I'm looking it up. So just to compare, so of course, the name 1, 2, 3, 4, 5, 6. So cyclohexa and then known versus this methyl cyclohexane. And their molar masses are extremely similar. So I think they're both 98, roughly, grams per mole, except the boiling point. Let's see, for methyl cyclohexane is 101. So this boiling point is a 101 degrees C, and cyclohexanone boiling point 155. So yes, indeed, we were able to predict just based off of polarity. So ketones can also be used to detect diabetes. So for example, acetone. You could even train a dog, for example, to detect the presence of ketones and then be used to, diagnose when someone with diabetes is undergoing ketosis. So that's why their product would be a ketone. So let's look at some reactions now. So looking at, let's look at the oxidation mechanism first. This is reduction. And we covered some of this in our alcohol chapter. So if you remember, we could oxidize some of our alcohols to ketones and then take them further. And so aldehydes. They can undergo oxidation. So oxidation of aldehydes. So we have our aldehyde. Can be oxidized to our carboxylic acid. So some example. So let's look at butanol. So 1, 2, 3, 4. I think I have too many carbons. So 1, 2, 3. Oh no, that's right. 1, 2, 3, 4. And then so let's add it with potassium dichromate. And so then it would oxidize it to our butanoic acid. So 1, 2, 3, 4. Now what if we reacted it with this one? And we tried to oxidize this species. So what would happen? And so this one here would be no reaction. And so if we would like to oxidize this, then we have to use a different reagent. And so only aldehydes react with Toland's reagent. And so this is useful. So let's talk about this. So Toland's test. So this is called a mirror test. And so ketones do not react. And you could try, so 1, 2. You have hexanol plus silver oxide. That put too many in. That's fine. OH, and then plus silver. So this is a nice test, since if you were to do it, it plates out silver. So this gives you what's called a mirror test. You would get all this plating of silver, and then that would be a positive test, knowing that you had an aldehyde. And so now let's look at reduction. So reduction is the opposite of oxidation. So we can take our carbonyl group and reduce it. Then 2 hydrogens are added. So you have one on the O here, another to that carbon. So aldehydes are reduced to primary alcohols. So you can see that, right? Carbon bonded to one carbon over here. So this is aldehyde reduced to primary alcohol. Looking at this ketone, to now be reduced to a secondary alcohol, since this carbon is attached to two R groups there. And so you can use different reagents. So let's do one. And so let's do a reduction. So we can do hydrogen and palladium. Now this becomes a OH. And H there. Now we have our alcohol. Can do another one just to compare. So now going back to cyclohexanone, adding hydrogen and palladium. So we break that bond, break our double bond. This becomes our OH. We add another hydrogen here, and so that's our secondary alcohol. Your book has a lot of biological connections. Let's look at the next category, acidyl formation. This is important. So we can react aldehydes and ketones, undergo reactions with alcohols. So react aldehydes and ketones with alcohols to form hemiacetals. So to define, let's first define, well, what's what? So a hemiacetal is going to be carbon OR OH here, and then an acetal is going to be carbon OR OR. So the only difference, this has a terminal hydrogen. These are just connected to other R groups. So now looking at this, we can start with ethanol as our alcohol component. So starting with our aldehyde. So propanone here. So now we're going to react it with our alcohol in the presence of an acid. So that's ethanol in the presence of sulfuric acid, so a strong acid. So let's look at the mechanism, even though your book doesn't go through it. So we're starting with this species. We're in acid conditions. So what's going to happen first? So we have our oxygen, it has our lone pairs on it. We have water. And I'm going to take, so you could draw it, it's best to draw it as hydronium. I'm kind of trying to take a shortcut here, draw it as H plus. So this water, this oxygen will pick up H plus, become protonated. And so now oxygen has a positive charge like this. Water, our alcohol now will go and attack. So we have ethanol here. Again, oxygen with its lone pairs. So it's going to go ahead and attack that carbon, because remember, this is electrophilic. It wants, or this is, the carbon is electrophilic. These electrons want something nucleophilic, aka something positive. And so they're attracted to this carbon. Now that it's made a bond here, these electrons have to go somewhere. So I push them onto that oxygen. So let's draw this out. So carbon, hydrogen, OH here. And then now we have our alcohol attached. So draw that on. Now that's a positive charge. So now we're here. Now we just need to have water deprotonate. The water comes along, deprotonates this. And so now we form our hemiacetal here. So our product. So now we're here, right? So this is our hemiacetal group. And so what we could do, starting here, we can add another equivalence. So let's start here. So we're starting here. This OH can be protonated to make it into a leaving group. Now we're starting with our hemiacetal. I'm going to switch colors. So I'm just going to rewrite it. So now we're starting with our hemiacetal group. So it gets protonated again, because again, we're in acidic conditions. So it is protonated. So now this makes it water, which is going to be a good leaving group. So now we're sitting here. Oops, sorry, I didn't draw those. And so now what can happen is this group, our alcohol here, can reform our double bond. So this causes the elimination of water. So let's draw that product. So carbon H still attached. Now double bond O. Then we have this product. This has a positive charge on it. Again, we lost water. And so now we have another nucleophilic addition that can happen. So we have our carbon here. Oxygen wants those electrons. So our alcohol can attack again. So let's do that. So attacks our carbon. These electrons go back up. So now we have carbon, hydrogen. Now our other alcohol. Oops, sorry. And so this is no longer positively charged, right? It has all its happy electrons there. This is positively charged. And so last step, we just need to deprotonate this so water can come along and pluck off this hydrogen. And so now we should have formed our acetal. So now we have 2 alcohol groups on there from our ethanol. And so this gives us our acetal species. Any questions about that so far? So let's look at your homework and look at some practice problems. Again, ask questions. This is your time. Give me 1 second. Let me send it to OneNote. There we go. And so looking at this, sorry, I didn't copy into the right one. There we go. So looking at our homework, this is funny. So the first one, which of the following combinations of chemicals can react to form a hemiacetal? So we just did this one. And so which answer is it? So a hemiacetal, we need a aldehyde and an alcohol. So B. And then so an oxidation product of an aldehyde is, so we said that aldehyde, that makes that carboxylic acid. And then the reduction product of an aldehyde, so what do we make? We started with an aldehyde. And then we were able to reduce it, convert those bonds. We made an alcohol. So which of the following will not be readily oxidized by KMnO4? So this might take a while. Start drawing out some structures. So 2-propanol. So OH. So there's still a hydrogen there. This is a secondary alcohol. So 1-pentanol. So I can tell that's going to be a primary. So 2-methyl, 1-propanol. So propanol. So 1, 2, 3 there. So 1 for my OH. So that's still good. So that's a primary. Let's do 3-pentanol. So pentane. So 1, 2, 3, 4, 5. 5. So 3 OH. So that's going to be a secondary. And then 2-methyl 2-butanol. So 1, 2, 3, 4. 1, 2, 3, 4. So 2, 2. So methyl butanol. So there's no H here, right? There's no hydrogen. So this is going to be a tertiary one. So this is going to be the most difficult. So E. Skip naming. Oh, this one might be interesting. So this looks like some sort of ring with an aldehyde group on it. So this is funny. At least I think it's a funny compound. And so how would we name this? So this is in one position, right? So now this is 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Pentachloro benzaldehyde. Let's do some of these next. These look good. So draw our hemiketal that is formed in the reaction of butanone with methanol. So looking at butanone, so this is a ketone group. So 1, 2, 3, 4. Butanone has to go here. And then plus methanol. And so what hemiketal will be formed? So remember, we're going to be attacking that position and adding the methyl on there. Or methanol, excuse me. There we go. And our OH. And so there's our product. So now let's draw the aldehyde that is formed in the reaction of methanol with potassium dichromate. And so name this aldehyde. So it's going to be oxidized. So we're forming our double bond. And so this would be methanol or formaldehyde. So let's try another one. 2-pentanol. So 1, 2, 3, 4, 5 with potassium dichromate. So forming our double bond. And so now this would be 2-pentanone. And so now we're going to do a hydrogenation or reduction reaction. So, oops. 1, 2, 3, 4. Oh, that's okay. Butanone. H2 catalyzed by palladium. And so now This is going to turn into an alcohol. And so now this would be 2-butanol. And then the last one, so draw the carboxylic acid that is formed with the reaction of propanol with potassium permanganate. No, potassium permanganate. I just got in the zone here. So KMnO4. So this would turn it into carboxylic acid, so propanoic acid. All right. Any questions or anything about this material? So just practice drawing your structures. All right, let's go ahead and end lecture here for today. I'll hang around in case there are any questions, and then just email me if you'd like to set up office hours or anything. Almost available. Don't forget, it's week 8, so we're almost done with the quarter. So thank y'all. Have a great day.